So now we look at another example. Okay, we look at, and this example, I don't think I don't think you'll be learning anything new in terms of formulation, but I want you to watch the procedure that I do, okay, because it will help you reduce. Come on, Eugene. It will help you reduce the possibility of making mistake. Okay, because I've done this problem from different textbook before, and I make some really bad mistake, and I found a way to stop making those mistakes. Okay, that's what I want you to learn. Okay, so you can see that the clamp has been tightening on wood planks glued together with a load P equal to 400 Newton. Determine in section AA the stresses at point A, okay, the stresses at point B, the location of the neutral axis. Okay, so looking at this problem, right? If we were to see how at AA, right? So if we cut this structure into two, okay, we chop it into two. And at this point is our AA, right? And you have a P over here, right? And you know the distance from here to here is your D, right? But we don't know where our E is here, right? So action equal to reaction, right? So if you look at, so if I'm going to draw my transformation over here. So this is my X, Y, rotation about Z. Okay, so this is my PX based on the transformation, right? So when that's the case, action equal to reaction, this is still my PX, right? So the moment will be coming, so relative to line AA, right? The moment will be coming down this way. So this is moment about Z, right? So this is compression. This is tensile. Okay, so over here, our counter moment, right? Newton's third law. This is moment about Z, right? So on top is still our tensile and compression. So from here, you know that on top is compression. Sorry, on top is tensile. So just write this, okay? So this is tensile, right? And then this is compression. Just write this down. So you are very sure now point D will be under compression. Yes or no? Right? So PX is going to induce a tensile, right? Okay. So some of you say, Eugene, what is, so wait, before I say Eugene, so we know that the formula is going to PX, stress X is going to PX over A, right? Plus by MZ over IZZ multiplied by Y. Okay. Now, one thing I want you to watch. If your applied force is above the centroid, okay, I want you to have a good practice that you take your datum or on this surface when finding your so this is the datum for finding centroid. Okay, you will make less mistake because once you find this E, right, Once you find this E, E is also equal to your what? So for this case, E is also equal to your what? Your big Y bar. Yes, Eugene, come on. So we know that E is also equal to your big Y bar. You just replace your E with your Y bar. If you take your datum down here, right, what will happen? You have to compensate. Okay, so don't make that mistake. I used to make a lot of mistake. So when that's the case, we know that this line over here is going to be your datum. Okay, when you find your centroid and when you find the position of your neutral axis. Okay, so we're going to apply this formula, and we also know that moment is equal to P plus by E or D plus E. Okay, we know that now. Okay, okay. So once we have, so in fact, if you look at our analysis, this is our analysis. Okay, this I mean this diagram we've drawn is the analysis of the entire problem. Okay, so we are able to identify that this is known as eccentric loading. Okay, this is known as eccentric loading. Okay, so now we know what formula to use, right? So we have to find simple stuff first. So we're going to find what is Px. Okay, so we don't know Px, we don't know A, we don't know Mx, we don't know IZZ. Why? Dependent on the what? The area. So do simple stuff first. Okay, so Px is equal to plus 400. Is it plus 400? Yeah, plus 400. Okay. So Px, why you put plus? You know that it's going to induce a what? A tension. Okay. Then the next thing we do is moment about Z. So moment about Z, okay, is equal to M or Px, right? Plus by D is equal to what? D, if you look at D is equal to 0.05 or 50 times 10 to the power minus 3 plus by E. We don't know what E is yet, okay? And this formula is true if the datum, okay, is taken from the top, okay? If you were to take the datum from the bottom, then the formula is like that. 50 times 10 to the power minus 3 plus by 0.02, okay, minus by E. Why 0.02? Because this is 20 meters. Because we decide to, this is not advisable. You want to take your data from here, okay? I will not advise you to do that. If you forget this, you're done, okay? If you forget to compensate, okay, you're done, okay? So this is datum is taken from the bottom, okay? So don't do that, okay? Don't kill yourself, okay? Now, from here, okay, so my preference, as I told you, is what? Okay, the data profiling central is dependent on where the applied force is relative to the what? Relative to to your centroid. Okay, where the applied force. Okay, so don't take it in the opposite side. Okay, so down here, the applied force is above the centroid. You take your datum below the centroid. You have to compensate. Forget it. Okay, don't kill yourself. Okay. Now, do you all want me to show how to calculate the centroid? Yes or no? Anyone? Or I can move on with that. I got no answer. Okay, I will show it. No answer means yes. Okay. Right? So we know, right? We are going, so based on this figure, this is our Y, this is our Z. Okay, so datum from the top. Okay, we're going to take datum from the top. I'm going to bite this into 1 and this into 2. Okay, so we're going to find centroid. Section, I'll try to do it quick, okay, because you guys know this already. 1 and 2. So because we are going to find I, Z, Z, okay, so this distance will be our width. This distance will be our depth. Okay, so this will be our width times depth. Okay, so the width is 10, the depth is 4. Okay, for the bottom one, the width is 4, the depth is 16. Okay, so this will be equal to 10 times 4, 40, 4 times 16, 64. Okay, so 10 times 4, 40, 4 times 16, 64. Then we have our y bar. So it's 4 divided by 2. This is 2. So 4 plus by 16 divided by 2. So 4 plus 16 divided by 2. This is equal to 12. Then we have our WD y bar. Okay, so this will be 80. 64 times 12 will be 768. So this will be 104. So 768 plus 80 is 848. Okay. So the y bar is equal to 848 divided by 104. So it's equal to 848 divided by 104. Come on, Eugene. 8.154. Okay, from the top. Okay, so if you want to do from the bottom, your answer is equal to 11.846 from the bottom. Okay, but I advise you guys already, it's best to take from the top. Okay, then you find IZZ1. Okay, so 10, 4, 3, 12, 40, 8.154 minus 2 squared. Okay, so 10 times 4 power 3 divided by 12 plus by 40 times by 8.154 minus 2 close bracket squared. So it's equal to 2.713 times 10 to the power 9. No, times 10 to the power 3, sorry. Millimeter to the power 4. Let me do it again. 10 times 4 power 3 divided by 12 plus by 40 times by 8 bracket 8.154 minus 2 squared. Oi, I get different answer. By 12 plus by 40 times by 8.154 minus 2 squared. I get 1.568. How did I get the first value? 1.568. Okay, times 10 to the power 3 millimeter to the power 4. Let me do it again. 10 times 4 power 3 divided by 12 plus by 40 times by 8.154 minus 2 close bracket squared is 1 point. Yep. So IZZ2 is equal to 4, 16, 64. Wait, do 64 properly. Come on. 64, 8.154 minus by 12 squared. Okay. So 4 times 16 power 3 divided by 12 plus by 64 times by 8.154 minus 12 squared is equal to 2.312. 2.312 times 10 to the power 3. Okay, let me do it again. 4 times 16 power 3 divided by 12 plus by 64 times by 8.154 minus 12 squared, 2.13. So I total, okay, is equal to 1.568 times 10 to the power 3 plus by 2.312 times 10 to the power 3. So this will be equal to 1.568 power 3 plus by 2.312 power 3. So it's equal to 3.88. What is somewhere? If axial is like, could it be tensile? If the axial is Curtis, the answer is yes, but it has to be only be just purely tensile. Okay, and the offset distance the E distance has to be very small. Okay, times 10 to the power 3 millimeter 4, or 3.88 times 10 to the power minus 9 meters 4.